This is my presentation on Physics 2, Lab 3, the magnetic field of permanent dipole magnets. The purpose of this lab is to measure the distance dependence of the magnetic field due to a small bar magnet using a Teslameter app on my phone. We will compare these measurements to the calculations with the Biot-Savart law given to us through our code to see how similar the values are. My findings have determined that the closer the magnet is held to the sensor on my phone, the stronger the magnetic field is. This distance dependence is related by a factor of r to the negative third. The value for mu, which is the magnetic dipole moment that I calculated from my data, was 3.45. I will further explain later how I reached this value. The procedure of this lab starts with lining up the smartphone so that the x value of the magnetic field without the magnet nearby is as close to zero as possible, so that later in the lab we're sure the magnetic field we're measuring is due to the bar magnet only and not influenced by the Earth's magnetic field. From this point, we can find the position of the magnetic field sensor on the phone by minimizing and maximizing the x and y values of the field through moving the phone both up and down and side to side. Once the sensor is clearly marked, we are able to proceed with the rest of the lab. I placed the bar magnet aligned with the sensor and measured where the x component of the magnetic field due to the bar magnet was 1,000 microteslas. After finding this distance and repeating 3 times to help eliminate human error, I also measured the magnetic field at a distance 1.5, 1.75, and 2 times this distance. I then converted by overall averages for each distance into teslas. My results in a table are shown here. After plotting this data into a graph of natural log of magnetic field versus natural log of distance, I found my data to be almost linear. From the equation of this curve, I found the value for n to be the slope of the graph, which is negative 3.07. I was also able to calculate the value of k, the constant in this equation, by observing the natural log of k is negative 14.18. I then took the exponent of this value to find the value of pure k, which is 6.9 e to the negative 7. To calculate the value of mu, I took the equation k equals mu naught over 4 pi times 2 mu and rearranged it to solve for mu. I use this equation with the factor of 2 included because it is the equation for an on-axis dipole moment, just without the distance cubed in the denominator. I found my final value of mu to be 3.45. I found my distance dependence to be an exponent of about 3 in the denominator, referencing the equation given to us in the lab, b equals k times r to the n. This is the visualization of my lab through code on VPython. I edited the value of the magnetic moment I calculated by hand and added code to create an arrow at a 45-degree angle in relation to the bar magnet. After scaling my arrows to make everything appear, this is the picture I arrived at. The final calculated value for the magnetic field at a parallel location is 6.9 times 10 to the negative 4 Tesla in the x component. The B field at a perpendicular location is negative 3.45 times 10 to the negative 4 Teslas in the x component. And the B field at a 45-degree angle is 6.09 times 10 to the negative 5th in the x component and 1.8296 times 10 to the negative 4 Tesla in the y component. When I found the 45-degree angle through a physical experiment, I reached a rough B field of 9.2 times 10 to the negative 5th in the x component, 4.5 times 10 to the negative 5th in the y component, and that unit is Teslas. I found this value by taking the y component of the magnetic field when the x component was equal to 0, which I got to be 18 microteslas. I then subtracted this value from the y component of the magnetic field when I rotated the magnet 45 degrees, all at a distance 0.1 meters away from the sensor, which is the distance the code specifies. I did this subtraction because when the magnet is not exactly parallel to the sensor on my phone, the magnetic field of the Earth is also measured in the y component. If I subtract the value of the magnetic field of the Earth, I am left with the magnetic field due to just the bar magnet. I am also subtracting the magnetic field due to the Earth in the x component, but this value is just 0, so the magnitude does not change. The value I arrived at experimentally is almost equivalent to what our code calculated. excusing a margin of error due to imprecise angles and the slight influence of the Earth's magnetic field. If we hadn't oriented our compass to account for the magnetic north, the total magnetic field would be the addition of the bar magnet and the magnetic field of the Earth. This would have given us entirely different values for our distance dependence, which would have not been accurate. If we were to stick two identical bar magnets together end to end, the measurements for the magnetic field would be exactly the same. I actually did this experiment out, and this is the conclusion I found. In conclusion, the distance exponent in the Biot-Savart law and the distance dependence computed by hand are equivalent. My computed value for mu was 3.45, and for n was negative 3.07. Overall, my computer model with the Biot-Savart law reflected the physical values I calculated when I did the experiment out myself.